Hi everybody, and welcome back for the video for lesson 9.5, which is all about volumes of revolution, so the same thing we've been working on, only today we're going to be revolving around other axes. So we're not going to be using the x and the y axis anymore as our axis of revolution. So here's the big idea of today. So far, we have only revolved our regions around either the x-axis or the y-axis. And today, what's going to change is that we're going to start revolving our regions around other horizontal and vertical lines on the graph. Now, in general, here's what we're going to kind of use as our guideline. Anytime we're revolving around a horizontal line, which a horizontal line is going to be similar to the x-axis on the graph, it's going to be horizontal. We are going to integrate with respect to x. Now, anytime we're revolving around a vertical line on the graph, which is similar to the y-axis, it's going to be a line that's up and down, we are always going to integrate with respect to y. So I always remember that because if the line we're revolving around looks like horizontal, like the x-axis, we use x for our integral. And if it's vertical, like the y-axis, we integrate with respect to y. So let's go ahead and try an example. Now, part of the issue that has been coming up recently is that reading carefully is really important here. So let's make sure we highlight and realize like sort of what given information here is really important to recognize. If we're finding the volume of a solid formed when the region bounded by the graphs of y equals the square root of x, so I know I'm going to need to graph that, and y equals x squared, is revolved around the line y equals 1. So I need to draw a picture where I can see both of those graphs, I can see their intersection point, and I'm going to revolve that region around the line y equals 1. Let's go ahead and sketch that graph. So if we've got a graph, I meant to use a pen tool and I used a highlighter tool. So if we've got the region bounded by y equals x squared and the square root of x, y equals the square root of x is a graph that looks like this. And y equals x squared is a graph that looks like this. Now we're going to find where those intersect, and I've graphed this enough times to know that these two graphs intersect at the point 1, 1. We're going to take that region, so this region bounded by those two graphs, so contained in here, and we're going to revolve it around the line y equals 1. Now y equals 1 is a horizontal line on the graph, and that's going to be my axis of revolution. So I'm spinning this region around this line. Now, if I do that, if I spin this region around this line, the image, the other side of the region would end up looking like this. And because I'm revolving, I'm going to end up with circular slices. I'm going to draw in one slice here. So if I look at this slice, for example, right here, and I revolve this slice around that line. And you'll notice I'm drawing my slice, I should mention this, in the original area that I started with before I revolved. I'm not drawing it in that pink area up at the top because that's just the image of what I'm revolving. If I draw one slice here, the slices are going to be circles, and there's going to be an inner and an outer circle because there's going to be this gap in the middle. Because of that, I can determine the first thing that I need to know, which is that this is going to be a washers problem. We're going to end up with slices that look like washers. Now, when I have a slice that looks like a washer, I'm still going to use my area formula, pi r squared, like I did before. And just like we learned in the previous lesson, I'm going to really need two r's here. I'm going to need a big R and I'm going to need a little r. Now my big R is going to be the distance between the axis of symmetry and the outer edge of my area that I'm revolving. That's going to be my big R. And my little r is going to be the distance between the axis of symmetry and the inner edge that I'm revolving, sort of that inner circle. My big R can be calculated by doing top minus bottom. In this case, the top of this region is the line y equals 4. The top of that's that radius. So my big R is going to be 4 minus the green function, which is x squared. My little r is going to be, oh, I'm sorry, it's not 4, it's 1. What am I saying here? My goodness gracious. It's 1 minus x squared. I apologize. I'm misreading the question really quick here. 1 minus x squared. Now my little r is going to be that pink line again minus the blue function I graphed here, which is the square root of x. When I use that information to set up my volume is going to be set up using two integrals. The first integral is going to integrate from 0 to 1. Those are the x values from 0 to 1 of pi times big R squared, which is 1 minus x squared squared dx, minus my second integral is going to be the integral from 0 to 1 of pi times little r squared, which is 1 minus the square root of x squared dx. And if I type all that in on my calculator and I evaluate my integral, the actual volume that I get here is 1.151. Let's look at another example. So that example was when we were revolving around a horizontal line. In the next example, we're going to be revolving around a vertical line. Now, we want to find the volume of the solid, and again, we're going to read really carefully here. Formed when the region in the first quadrant bounded by the graphs of y equals the square root of x and x equals 4 is revolved around the line x equals 5. So I'm going to go ahead and sketch a picture so I can visualize what's going on here. So I know I'm going to be in my first quadrant. I'm going to be taking y equals the square root of x, which looks like this, and the line x equals 4, which is going to be a vertical line at 4. And I'm going to be revolving this region. Now, these two graphs are going to intersect at the point 4, 2. And I know that because if I plug x equals 4 into the square root of x equation, I can figure out that the y value where those would meet would be 2. Now, I want to take that region and I want to revolve it around the line x equals 5, which would be right here. So this is going to be my axis of revolution. When I revolve this region around that line, the sort of image of this region would be over here. And if I look at one slice, so I'm going to look at one slice of this region. I'm going to look at this slice right here. When I revolve this, I'm going to end up with a circle with a hole in the middle. Which means when I set up this problem, I'm going to be setting everything up using the idea of washers. So I'm going to have a big R and I'm going to have a little r. Now my big R is going to go from the axis of symmetry to the outer edge of my slice. And my little r is going to go from the axis of symmetry to the inner edge of my slice. So let's go ahead and start by writing down the formula area equals pi r squared. Since each of my slices here is going to be shaped like a circle because I'm revolving something, I'm spinning it in a circle, I'm going to use my circle formula, which is pi r squared. Because there is a gap in the middle, I'm going to need a big R and I'm going to need a little r. In this case, my big R is going to be, I'm going to use the idea of right minus left. The right side of that big R radius is the line where x equals 5, and the left side is the blue graph. Now, the problem is that my original blue graph equation is not in terms of y. And I'm going to need this to be in terms of y because I'm revolving around a vertical line and I'm doing right minus left. So I'm going to go ahead and I'm going to rearrange this a little bit and I'm going to make it x equals y squared. And so I'm going to write 5 minus y squared here. Now my little r is going to be the distance between my axis of symmetry, which in this case is still 5, minus that green graph, which is just 4. And I can actually just simplify that to 1 because 5 minus 4 is 1. Now when I set up my volume here, I'm going to integrate from 0 to 2 because my y bounds go from 0 to 2. And I'm going to have pi times my big R, which is 5 minus y squared, squared dy, minus the integral from 0 to 2 of pi times my little r, which is 1 squared. If I type all that into my calculator, I get that the volume of my solid is 87.126. All right, last but not least, let's go ahead and look at a problem where you do have to make a choice. So this is going to be a problem where you're going to have to decide, is it a horizontal line, is it a vertical line that we're revolving around, and how do we set up the formula in that case? We want R to be the region enclosed by the graph of f of x equals x to the fourth minus 2.3x cubed plus 4, which is shown on this picture here, and the horizontal line y equals 4, which again is shown on this picture here. So we've got this horizontal line, and we've got the f of x equation right here. We want to find the volume of solid generated when r is rotated around the horizontal line, y equals negative 2. So I'm going to go ahead and add that to my graph to give myself a visual. Y equals negative 2 would be down here somewhere. Now that's going to be my axis of revolution. So I'm going to be revolving this region contained between those two graphs around that line. If I sort of visualize where the image of this region would end up, it is going to end up below this line. So it's going to end up somewhere down here. Now, if I picture one slice of this, so if I look at one slice of the original region and I revolve it, I'm going to get an outer circle and an inner circle because there's this big gap between the axis of symmetry and where the actual slices of my region start and stop. Therefore, because there is a big gap, I'm going to use a big R, which is going to be the distance from the outer edge of my slice to my axis of symmetry. And there's going to be a little r, which is going to be the distance between the inner edge of my slice and the axis of symmetry. Now, I'm still going to use the area formula, area equals pi r squared, because obviously my slices are circles. And big R and little r, I'm going to list separately because I know I'm going to need two separate integrals here. Big R is going to be the top minus the bottom. In this case, the top is the green function, which we were told in the directions is y equals 4, minus the bottom, which in this case is negative 2. So I'm minusing negative 2. That does simplify and just become 6. Little r is going to be the distance between the top of that little radius, which is my f of x function, minus the bottom of that little radius, which is the horizontal line negative 2. And again, this does simplify because I'm minusing a negative. I'm just going to simplify that to f of x plus 2. Now, if I set up my volume is going to be the integral from 0 to wherever these points intersect. Now, if I graph this on my calculator, I can find that the intersection point is 2.3 comma 4. So I'm going to be integrating from 0 to 2.3. Pi times big R squared, in this case that would be 6 squared dx, minus the integral between 0 and 2.3 of pi times little r squared, which in this case is f of x plus 2 squared dx. If I simplify this and I type it into my calculator, I get 98.867 as my final volume. All right, thank you guys so much for watching. Don't forget to try the practice for this, and I'll see you soon.